Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. Today we are joined by Doctors Lisa Rueschhoff and Matt Dickerson to discuss polymers, high-temperature ceramics, and how materials research impacts our everyday lives.
In 3, 2, 1.
Dr. Lisa Rueschhoff and Dr. Matt Dickerson, welcome to the podcast.
Thanks for having us.
Yeah, thank you, Michelle. Thank you for having us. It's great to be here. Excited to talk today.
Yeah, and we're excited to have you too. Now, you're both materials researchers within the Air Force Research Laboratory, specifically our Materials and Manufacturing Directorate. And we're going to dive into your careers and cool things. But just to kick it off, I'd like to say that I think material science is a really underappreciated field because materials are all around us. And a lot of them, unless they're a completely natural fiber, had some science go behind it. So starting off, just to throw you a huge question, what would you say one of the most important discoveries in your field is?
Yeah, oh my gosh. Yeah. So Michelle, we're starting off with the late questions here. As you said, I mean, material science is all around us. Really, every material we touch has to be engineered. And different periods of human history have been defined by the materials we use, right? So the Bronze Age or the Iron Age. But just to focus that question down a little bit, just to my small little portion of material science, Lisa and I work in the area of high temperature structural ceramics. And so in that realm, what I would say one of the most significant breakthroughs has been some work that took place in the late 1970s by a researcher called Yajima. So this research out of Japan, they did some really interesting stuff. They were able to take a polymer precursor, spin that into fibers, and then transform those polymer fibers into high performance silicon carbide ceramic fibers. And those fibers are really important today for things like jet engine applications and possibly nuclear reactors, all sorts of applications. So yeah, those breakthroughs of the pre-ceramic polymers, so polymers that turn into ceramics, and the ceramic fibers, both really incredible work.
Yeah, I definitely agree with what Matt said and what you said, Michelle, at the start. There's so much around us in materials and so many advancements that have been made. But just like Matt, my head directly goes to the materials we work on, which is high temperature structural materials. And just like Matt, the first thing I thought of was fibers. I wasn't thinking the making of fibers. That's a huge advancement, but I was actually thinking just the incorporation of fibers into these brittle materials. The idea and the concept of actually reinforcing these brittle materials with fibers and making these ceramic matrix composites, I think is the biggest advancement in our specific field for sure. There's been lots of other big, great ones, but that one's kind of hard to ignore, I would say. And I know that we're going to get into a lot of those details later as well.
Speaking of advancements, we can narrow it down to maybe your guys' careers. How did, starting off with you, Lisa, how did you end up at the Air Force Research Laboratory and what's your background?
Yeah, so I started here 5 years ago now, and I came here directly out of my PhD from Purdue University. And so that's really only about 3 hours away. I was close by, but I hadn't had too much interaction yet with AFRL. And I actually came here through a fellowship program called the NRC Postdoc Fellowship. And so I came here to work on that fellowship, and actually Matt was my research advisor. And so that's kind of the program that got me in the door at AFRL. And I loved my experience so much that I decided to stay and take this position as a civilian on the team. But that's at least kind of what brought me here. Before Purdue, I was at Iowa State University and got my degree in materials engineering.
Did you always think that you would be a materials researcher?
No, not at all. And I really didn't even decide on materials till probably my second year of college and undergrad. At Iowa State, they allowed you to select something called undeclared engineering. And that's when I decided, but I kind of got pushed into this box of people who don't, I guess, you don't know what you want to do, you got to figure it out. And so I went around to all the different departments trying to figure it out. And that's when I really landed on materials. But definitely growing up, I wasn't the kind of person that was, I'm really into science. I know when I grow up, I want to be an engineer. I was really interested in debate and things like that. And for the longest time, I thought maybe I'd be a lawyer. For a while, then I thought maybe I'd be a doctor. I think what really drew me to engineering, though, was the idea of problem solving. So as much as I loved debating and kind of being in those sort of situations, I really loved doing and making things happen. So it wasn't the traditional route of saying oh, I'm amazing at math and science, and those are my absolute favorite subjects in the world. I mean, I excelled at those, but it wasn't my passion, but that's kind of at least how I got there.
And I'm curious too, with going through there, I know a lot of what helps people decide what they're going for is a great mentor. Was there any teacher that really stuck out in college that was like, you know what, materials is pretty cool. Let me show you some experiments, and the rest is history?
Yeah, absolutely. Actually, it even started in high school. We didn't really have like engineering courses, but our physics class was the closest thing. So I had an excellent physics teacher who really started us thinking on those kind of engineering problems. And that kind of clicked for me, at least on engineering. But once I got to Iowa State and we got to go around and see the other departments, there were some faculty there who gave a lot of the demos on the science. So there was a professor, Professor Gianello, because I still remember the really cool demonstrations he did. One of the really cool ones is he had a pane of glass that was tempered, and he would like jump up on it and show that it couldn't break, and then clip it on the side and it would completely like violently shatter. That was really cool. It was kind of like seeing those things in action. I was like, I want to do that. So yeah, that was a big part for sure.
Truly a window into science in many ways. that is super cool. So we're going to flip the script then and go to Matt. So Matt, same question. What really got you into the materials world, and how did you connect with AFRL?
Great question. It's a little hard for me to actually go back and think about the first time I was interested in STEM. It's been kind of just, with me throughout my whole life. So as from the earliest ages I can remember, I was interested in science. I love reading books about astronomy and biology. My parents were very supportive. I remember going out into the sandbox, setting up building the volcano out of sand, putting the little volcano reaction in the center and doing that. And, also one of the really cool things I got when I was a kid was kind of a toy microscope, which is great, being able to see kind of the finer scale of life and some other materials. Yeah, so I made my first connection with AFRL actually when I was doing graduate work at Ohio State under Professor Ken Sanders there, who is a great ceramic engineer. So we actually started a project working with what are called diatoms. So diatoms are unicellular microalgae, and they make these really cool cell walls out of glass instead of things like cellulose. Really beautiful shapes. The Victorian people actually used to make little art out of them under microscopes. And we were doing work using those glass shells to change the chemistry and make some cool ceramic bits. But having a background in biology, I was really interested in how biology made those kind of ceramics, right? So for us to make glass, you need high temperature furnaces, whereas biology is doing this, at basically room temperature. So I got really, really lucky. My advisor made a connection and started collaboration with some researchers here at the base in the bio group. I really jumped at the chance to be able to work with them collaboratively. I commuted back and forth between Columbus and Dayton for a year. Before then, I moved to Georgia Tech to finish my PhD. But I was really impressed with just the awesome quality of people and research that was done at AFRL. So I chose to come back and work in the lab, again, under that same kind of NRC fellowship that Lisa did after I graduated.
Wow, I had no idea that algae could be so cool. Like diatoms making their own glass at room temperature, because earlier on, different episodes of this podcast, I thought, oh, wow, photons are really cool. But now, algae might be my front runner now.
Yeah. Algae, sponges, there's all sorts of things that make glass out there in nature. It's pretty cool.
Well, that's what I'm glad you said that, Michelle, because I'm curious. So with diatoms, how do they do that at room temperature? Like, are you able to break that down biologically? Like how do you build a cell wall out of glass?
Yeah, so it's still, still being worked on, still an open research question. The diatoms are pretty amazing. They're able to concentrate dissolved silica from the environment, and they use specialized proteins to guide the formation of the glass then.
That's awesome. That is such a cool snapshot into nature and how it ties into a lot of the work you're doing now with materials.
Yeah, absolutely. There's a lot of ties between biology and material science. So they operate under the same kind of central dogma, which is chemistry and structure dictate properties. So that's true whether it's an enzyme or whether that's a block of aluminum, right? So get the chemistry wrong, get the properties wrong, get the structure wrong, and you're going to end up with the wrong properties.
So I'm glad we started breaking this down, because I wanted to shift back to Lisa and start discussing what you're both doing now within the Materials and Manufacturing Directorate Ceramics branch. So can you kind of go into what your day-to-day looks like and what exactly the ceramics branch is all about?
So we work on ceramic matrix composites, or CMCs, and that's where we have a fiber that's acting as a reinforcing phase into an otherwise brittle ceramic matrix. So that's kind of the general scope of it, but that's not the only thing we do. There's a lot of other research that goes into it. And I would say both Matt and I work on everything from really basic science to discover the fundamentals behind this field to things that are more applied, to taking these materials and thinking about real life service conditions. So for myself, in terms of day to day, it really varies. So normally a lot of my time is meetings. So either that's meeting with postdocs to hear about their most recent discovery in the lab and offer some suggestions. It might be meeting with a really big team of researchers on larger programs that I work on. They might be at Eglin Air Force Base or over in a different directorate at AFRL. And we're talking about maybe the next test that we have coming up on a program. A lot of that is meetings. When I'm in the office, I like when I can get in and get to go into the lab and see what people are doing and kind of direct that. But yeah, it really varies. Sometimes we'll be at program reviews and be, at conferences. It's all over the place.
Yeah, that was a great answer, Lisa. I mean, that was a great overview. My answer is going to be much more granular, right? So when Lisa and I began our careers both, we spent a lot of time at the bench. So in that role, you're spending your time actually making materials, doing the processing, characterizing those materials by some of the advanced characterization tools we have, whether it's electron microscopes or different analytical tools, and doing functional mechanical testing, right? So over the years, my role has changed. And so I'm no longer at the bench so much. But as Lisa mentioned, we both oversee and lead research. So we've gone from really being that awesome person in the orchestra who plays the violin, right, to now being more the conductor of the orchestra, right? So overseeing the work of a lot of different people, a lot of different instruments playing different disciplines. And that, as Lisa mentioned, that takes a lot of communication, right? So that's where it's at. Being able to tie together different researchers in these large efforts, which requires communication by meetings, whether that's in person or online, phone calls, one-on-one discussions, and emails. But yeah, it's a fun environment to work in.
And I love that analogy. I'm glad you guys painted that with the conductor at the band. I was going to ask to see if you guys were kind of like the overseers or what it looked like from the top-down view, but that really made it come together. And I want to continue that by talking about a lot of the trends you guys are seeing. And of course, a lot of that's in ceramics. So I'm curious. So starting with you, Matt, we'll continue. Why are these high temperature ceramics so important for the Air Force? And what are you guys doing with them?
Yeah, so great question. I mean, when we talk about ceramics, right, most of our daily interaction with ceramics happens in places like the kitchen, right? So we have our ceramic coffee mug that says "World's Best Dad." We have the teacups and plates and these kind of whitewares. And so we're familiar with some of the properties of ceramics, right? They can handle high temperatures. They're fairly hard, but some of the major differences between the ceramics in your kitchen and the ceramics that we work on, how brittle they are. So my World's Best Dad coffee mug, right? Fantastic for drinking coffee. But if I drop it on the floor, it's going to break into, 1,000 pieces, unfortunately. A lot of the work that we do is how to bring greater toughness to those ceramics so they can be used for Air Force applications. And getting to that, the applications we really care about in our line of work, so high temperature structural materials, really deals with how can we produce high temperature materials that can increase the performance and efficiency of things like propulsion for the Air Force, whether that's jet engines, rockets, or other propulsion platforms, having aerospace vehicles which can take the heat, as well as other applications.
Ken, your mug actually says "World's Best Dungeon Master," right?
That it does. For many of our listeners out there, I love D&D, and I do have actually my D20 mug is right next to me. That's not a lie. So I've got ceramics around me right now.
Yeah, but also super important things to make planes or spacecraft be able to go really fast without burning up, essentially, right? Is a ceramics use.
Yeah, so exactly as Matt mentioned, the biggest difference in what we do in our kind of advanced ceramic materials from just the regular kitchenwares, the mugs that are brittle, is adding those fiber reinforcements. So these fibers offer a greater increase in toughness than what we would normally have. So meaning it doesn't fail as catastrophically. So if a mug, you drop it, it'll just shatter into a million pieces. The fibers actually give us what we actually call it graceful failure. So rather than being so catastrophic and being a huge detriment to kind of the component, these materials can fail in a way that isn't as catastrophic and aren't as damaging. But those fibers really add it's kind of a bridge that holds everything together. So that's really the traditional way that we toughen ceramics. And there's all kinds of ways that you can incorporate fibers. So traditionally you would have like a woven fabric. You can kind of lay that up and that gives you your fiber architecture, we call it. You can also add in smaller reinforcements. So maybe we call them chopped fibers or just individual fiber phases that add in. That makes it a little more easy if you're doing more complex shaping techniques, like with additive manufacturing. People even look at the smaller scale, adding things in like nanotubes or nanofibers. There's all kinds of different reinforcements, and it really just depends on the type of properties that you need.
That's really cool. I've heard of a lot of different applications of ceramic strengthening, things like, with Kevlar vests being used for defense when it comes to people out in the field. And my mind always goes back in history of thinking about, Grecian pots and others. There's things that even they could have done had they been able to weave stuff in there to make these stronger. They were very brittle, but still used for a lot of common purposes. So I'm interested, Matt. We learned a lot about different fibers and things and nanotubes that can strengthen these. Is there anything else your team is working on or other aspects of that to make these ceramics more durable?
Yeah, absolutely. Great question, Ken. Fibers are kind of the traditional methods, right? You mentioned in ancient history, we can go back to, putting straw and bricks for Egypt. Drawing on that thread a little bit, right? So we think about Egypt and architecture of pyramids, right? So one thing we can really do that's pretty cool is architect materials on the nanoscale. And so this is a really an emerging field. It's something that our team has worked on, is really how do we control the nanostructure of ceramics to be able to control their mechanical properties, for example. So when you start to shrink materials down from the bulk scale to the nanoscale, some really interesting things can happen, right? So in the case of ceramics, projects we've worked on by controlling the scale of the ceramics through actually self-assembly of specialty polymers, can get that ceramic structure down to about 20 nanometers. And when you do that, the ceramics begin to behave again differently, right? So in this case, actually, with a study that Lisa was the first author on, she found that you could actually compress these ceramics because they're nanostructured about 15%, release that pressure, and they fully recover, right? So it's pretty remarkable to think about. It's really outside of our outside experience, right? Going back to our coffee mug, you press on your world's best dungeon master coffee mug, and that thing's not going to compress, right? And if it does, it's not going to come back. So again, you can use that kind of behavior for the benefit of the Air Force and the greater DoD in the future.
Yeah, definitely don't want to roll the odds of that mug. Don't want it to be compressed. So with that being said, with a lot of these amazing materials, and this sounds like really high-end testing, you have to have pretty either high temperature environments or ones with a lot of intensity surrounding them. So I'm curious, Lisa, what kind of facilities do you have to make these stronger materials, or at least test to make sure they're ready to go?
Yeah, that is a great question because it's a really complex answer, and it's one of the most difficult things that we have to deal with because of how extreme these environments are. And when I say extreme, I mean a lot of different conditions. So we have things like really high pressures, we have really high temperatures, we have really high structural loads, we have really fast heating rates, we have different ionic species that are present. So because it's so complex, there's not really one test, especially on the ground, that can test for all those things. So often what we have to do is do individual tests that kind of get us there. Obviously, if you wanted to do a flight test and actually fly your material, you could test all those things, but that's an incredible leap. It's an incredible cost. So what we're able to do is kind of walk before we can run and do individual tests in the lab that kind of piece together each of those individual constituents. And then we'll kind of start to piece together those piecings together. So the biggest thing for us and our team is the temperature. Because that temperature is so high, and because the heating rate is so high, one of the main tests that we do to screen materials is what's called an oxyacetylene torch. So it's just like a torch that you'd use for welding. We control the flow of the gas in order to control the temperature of the flame. And we have a whole rig set up in our lab. It's really cool. We can set the material at a set distance away from that torch. And then we measure the temperature on the front and we measure the temperature on the back. And we see how hot it's getting and how quickly it's dissipating heat. And then see how it survives. We see, does it erode away? Does it totally crack under that pressure? All those kinds of things. And it's a great screening tool, especially for that temperature and that heating rate. Now, that doesn't give us everything. A lot of times we'll then take it to another kind of test facility, and we work with another research team within our branch called the composite performance team, and they do a lot of the mechanical testing. So that's where they really come in, is that mechanical for the structural load testing. So we'll kind of pair it with that to make sure that it can check all those boxes that I described before.
And for our listeners, an example, how hot is hot when you're talking about hot temperatures?
So we talk in Celsius, which is confusing because if you think about like your oven at home, that's in Fahrenheit. So we usually and routinely are going above 2000 degrees Celsius. That's what we would consider a really hot environment. We have a whole class of ceramics that are actually called ultra high temperature ceramics. And those are ceramics that have melting temperatures above 3000 degrees Celsius. So those are considered the top, right? If you know you're going to have this really extreme condition, that's generally the class of materials that you go for. But it is really hot. I can't stress that enough, that it's no other material generally can stand that type of temperature.
Oh, absolutely. I mean, that is, even in Celsius, that is eye-watering. And I think we may have kind of touched around this with different questions, but what makes ceramics, specifically what you guys are working with, so good with heat? Is it just it's good at dissipating? Like, what makes it so unique with that property?
Great question, Ken. So again, as Lisa pointed out, it's their melting temperature, but above and beyond melting temperature, for the things we work on, it's also the resistance to oxidation. So to oxygen, right? So you can have something that melts at really high temperatures. Like an example would be tungsten. So, tungsten's used in light bulbs or the old incandescent light bulbs. It has a melting temperature of about 3000 C, but if you were to break that light bulb and have that tungsten filament just out in the air, you plug that in, it goes to 3000 Celsius, it is going to have a plume of tungsten oxide coming off of it. So it's not just a high melting point, it is being able to form protective oxides or glasses on the outside of the ceramics as well. So again, it's as well as thermal conductivity, heat shock, a lot of other things we've mentioned.
Yeah, and actually, the thing I was going to add too is, as material scientists, we always think about things as their structure, properties, processing, relationships. So everything ties together. It always comes back to the atomic structure of a material. So the reason that ceramics have higher melting temperature than other materials is that they have stronger interatomic bonds. And so those bonds, as they become stronger, they're harder to break. And as you're melting a material, all you're doing is breaking the bonds in the atomic structure. And that is what makes them so hard to melt and to break down. But I always like to, everything ties back to each other. So I always like to connect those. But Matt's exactly right. It's like you could have something that melts really high, but if it can't withstand the oxidation, that damages your component as well. So it's all those things factored together.
First and foremost, interatomic bonds is a great band name, and I'm going to keep that one in the back pocket. And second, thank you for the breakdown. That's awesome. That makes a lot more sense in my head. And I kind of wanted to build that together about melting points, atomic structure. I mean, ceramics are cool. So, but something we've heard brought up here, or at least I'd like to go deeper into, is this idea of ceramic additives. Now, is that what you guys have already mentioned, like actually putting in fibers, nanotubes, or is this something different?
Yeah, so great question. Again, as far as aerospace goes, we see a lot of advancements coming from metals additive manufacturing and polymers additive manufacturing. In both cases, we can see that the complexity that's given to us by additive manufacturing is adding capability and reducing costs. So this is important for new systems as well as sustainment, especially for the Air Force, right? For ceramic additive, I mean, this is a research area that both Lisa and I work in, and this is a great place to be for the lab. Ceramic additive manufacturing is not quite as mature as metals additive manufacturing, but we have really a lot of potential in the future. So if we look at trends on how aerospace is playing out, there's more emphasis being placed on additive manufacturing metals for things like engines. But if we want to push those engines to higher temperature, we're going to need then to progress to a high temperature material, which this then puts us squarely in the realm of ceramic additive manufacturing. And so Lisa and I are both running projects in these areas. We have our own distinct directions. And Lisa, would you like to share anything about some of the exciting research your team's doing?
Yeah, definitely. I was going to add a few things too, because I completely agree about ceramic additive. There's so much potential for it. So like Matt said, we're sometimes seen as like a few steps behind metals and polymers. And that's just because the same properties that make ceramics really attractive, like their high melting temperatures and their high hardness, also makes them much more difficult to process. So it's not just as simple as, say, with a metal or a polymer, you could heat it up slightly and melt it and kind of form it into the shape you want. We can't really do that. So we have to kind of be able to process these materials into the complex shapes, and then afterwards do what we call sintering of them to get them to their final densification. So that's kind of where the difficulty comes in, and kind of ties into some of the different projects that we do. So some of the projects that I'm working on in ceramic additive, there's a couple different. One is incorporating fibers into the actual additive process. So like I said, that kind of helps toughen the ceramics. So actually incorporating fibers into a slurry that we then use the technique of what's called direct ink writing. So it's where you take a slurry and you extrude that out of a nozzle, but you tailor the rheology such that it can build up layer by layer. You think about extruding like a line of toothpaste, but it holds its shape. So then you extrude another line of toothpaste over it and you keep building and building. And what's nice is that with additive, you can really control the shape. You can make more complex shapes. You can also control the fiber direction because the fibers flow out of the nozzle and get aligned within that path. So that's something really interesting we're doing. We're also incorporating mixing within that process so that you can have two materials being printed at once, and you can control the ratio of those materials. So you can get what we call functionally graded compositions. So you kind of can control the actual composition of your material just on the fly while you're printing. A really big advantage of using additive manufacturing for ceramics is not just being able to make complex shapes. That's obviously a great added benefit of it. It also can allow you to really rapidly kind of screen different materials and compositions and to really cut down the time it takes to manufacture these types of materials. So in traditional processing of ceramic matrix composites, it can take months to year to make these kind of materials just because of the really in-depth processing that you do. So these kind of techniques would allow you to cut that down to kind of the week sort of time frame. So that just kind of describes one of the projects and one of the areas that I focus in ceramic additives. So I don't know if Matt, if you want to describe some of the other areas that are projects that you work in the area as well.
Yeah, absolutely. So I'd just like to point out one project we've been working on recently. Fantastic collaboration between the Air Force Research Laboratory, Harvard University, and UMass Amherst. And this is a project where we were using ceramic additive manufacturing to control the scale of materials from the nanoscale all the way out to the macro scale. So in this case, we talked about self-assembly a little bit earlier in architecting materials. And this project, what we actually did was to use an ink which contained a specialty polymer called a block copolymer, which will self-assemble into structures in that pre-ceramic polymer. So in using those specialized polymers together, we can actually control, again, the structure of the ceramics at the nanoscale. Then additive manufacturing allows us then to take that nanoscale material and control the architecture of that out through the micron and out to the macro scale. So again, really exciting project, great collaboration, and we hope that there's application for that for the Air Force in the future.
I'm glad you guys had a chance to not only dive into the importance and from what you said, Lisa, like really cutting down not only manpower, but just a lot of time when it comes to creating some of these materials. That's incredible how much that can change the game, if you will, and some other examples of what your teams are doing with it. So I want to go further and we'll go back to you, Lisa. Are there any other major projects or really cool stuff that illustrates what your team does from day to day, or at least cool success stories you want to share?
Oh man, that is a great question. I think we have all kinds of cool projects that we work on. It's hard to pick one and have one specific win for it. I already talked about the fibers that we're incorporating into the direct ink writing process. Another technique that we can do that's a little more advanced in terms of shapes that are possible is a technique called DLP, or digital light projection. And so what that does is it has a polymer resin that can be cured by UV light. So meaning that as UV light hits it, it solidifies. And so what we do is actually fill that polymer resin with ceramic particles. And then layer by layer, we project the outline of that slice onto a build plate. And so that it cures the material in that layer. And then you kind of can build it up, and then you're left with your structure. And what's really nice about it is you can get really complex features and really what we call overhangs or interconnecting features, something that would be hard to create with any other technique. And we recently got a new 3D printer in our lab called the Admatech system. And this is a really unique setup. I think when they installed it in our lab, it was the second one in the country that was installed. So it has a really large build volume. I mean, one of the projects that we've been looking at with that actually is with AFRL. They're really interested in creating ceramic components for turbine engines, like Matt already talked about earlier. And so we've been testing and printing some different turbine geometries with those ceramic slurries. And I think that's another really cool kind of project that we're doing. We're continuing it on with them and working towards actually printing a turbine that we could test with AFIT and with RQ, the different directorate. So that's another interesting one.
And that's huge. And I honestly wish I had some of the software and techniques you have now, because back when like 3D printing was really taking off in high school, I was in a CAD class where we had to design overhang hinge segments with printing. And I can tell you mine did not work. It was not made to the right size, and I had to do a lot of sanding. But that is so cool that you can have that level of precision and work on turbines. I mean, come on, that's a big deal. So I count that as a huge win. We'll go over to you then, Matt. Any other big wins for your team or cool projects you want to share?
Yeah, absolutely. I could talk all day about the awesome stuff my team does, from making new ceramic precursors to the additive manufacturing project I already discussed, where we're combining self-assembly with additive. But that actually kind of ties into something else, right? So we talk about using self-assembly to drive the structure of ceramics. That goes back to kind of biological principles, right? So self-assembly is one of the hallmarks of biology. And having worked between high temperature ceramics and biology, gives me kind of a unique perspective where I'm able to work with some of my other colleagues in bio, great collaborators over there and across the DoD in that area, and bring some of those principles to high temperature ceramics, whether that's bio-inspired systems. So if we're taking, let's say, the bonding schemes of specialized proteins, bringing those over to pre-ceramic polymers, using synthetic biology to create precursors for high temperature materials, or using biology to actually form a material. So there's a lot of interesting applications there. It's still very nascent, but there's a lot of power out there in the advances in biotechnology that can be applied not only to high temperature materials, but also creating a variety of materials and specialty chemicals that are DoD specific.
I mean, you hit right on a point I wanted to ask about, which is how your background as a biologist has helped your day-to-day work, and you just nailed it. So, I mean, I've heard about the bio-inspired team, how different, ways, like you said, self-replication. I mean, dragonfly wings. I mean, the way that certain facets of eyes work with insects. There's just so much we can learn from nature, and materials sounds like it's no different. So that's awesome. And again, I agree. We could definitely go in and out talking about a lot of the big wins, and I'm sure we may have another podcast doing just that. But before we get to that point, I do want to kind of curtail things here and go on to a point we like to always bring up at the end, which is, well, the idea of STEM communities and how they can connect. So I'd love to hear you guys' thoughts on mentorship and the importance in the field. We touched on what you said earlier, Lisa, about a really cool teacher in high school who really helped to invigorate your love for a lot of what you do, and especially in college. So do you guys have any mentorship, either advice yourselves, or have you seen great mentors that have imparted knowledge you'd like to share? And we'll start with Lisa.
Yeah, definitely. I mean, I think mentorship is so critical in every career path. So STEM is no different. I would say my original mentor was my dad, my parents being supportive. I know we touched on that earlier too, right? Just really pushing me kind of that's the original one. And I always think of that. I have a young toddler, right? So I think of that in terms of mentoring him to grow up. But for the field, I think it's so critical to build networks and to build those mentorships, both in and out of your place of institution. So Matt and I are both really active in our professional societies. There's one for ceramic materials, the American Ceramic Society, or ACER as we call it. And really getting active in that has allowed me to find mentorship outside of AFRL as well, which has been nice to have an outside perspective, and inside too. I think one of my big messages with mentorship when I talk to younger scientists is to have a really diverse set of mentors. It doesn't have to be something formal. You don't have to say, hey, will you be my mentor? But talking to as many people as you can, especially as you come to kind of life decisions or career decisions that you have to make. I always say that I try to be as unbiased as possible when I give people advice, but we're human beings. We're always going to have our biases. So my advice is to always talk to as many people as you can and kind of take in all of it and decide what's best for you. But I mean, apart from pointing out specific people that have been big mentors for me, I think that's just what stuck with me the most. I've been so lucky to have really excellent mentors. Matt was my first mentor here at AFRL, and just kind of expanding and kind of being able to talk to as many people as I can, I think has really helped me to get those different perspectives.
Yeah, I would definitely agree with that, Lisa. That's great insight. I actually like to expand on a point that you made, right? So I think that force mentorships, significant to the STEM fields. Great scientists aren't made by reading books, right? It's through these one-on-one interactions and actually working hands-on. AFRL also has a great formalized mentorship program you can take advantage of, but I also like to encourage people not to take such a narrow view on mentorship, right? So it doesn't have to be this traditional, I have an assigned mentor, this assigned mentor is senior than me, right? So it's, in the words of Isaac Newton, right? What I know is a drop and what I don't know is an ocean, right? So there's so much information out there that I don't know and better ways of doing things. I would encourage you to look at mentorship more holistically. It's really, to me, what you can learn from everybody around you, right? So that could be more senior personnel, that can be your peers, and that could even be people who are junior to you in the organization or wherever you're at, right? So this person might have as much overall experience as you. They might have greater depth of knowledge or insights in one particular thing that maybe you could benefit from. So yeah, definitely get out there, learn from your colleagues, learn from others in the community, and feel free to reach out to Lisa and I if you're interested in material science.
And I'd like to thank you both for joining us and teaching us just a little more about the huge world of material science. And hopefully we can have you back in the future.
Yeah, we'd love to. Thank you guys so much for having us. This has been fun to be able to talk about the things that we love. You can tell we're pretty animated. We love this, so we love to talk about it.
Absolutely. Thank you for having us. It's been great being on the show. Thank you.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.